Hello, everyone. Welcome to our video on games and game based learning. So, my name is Yuan Hao, and the focus of my section is rules systems, logical constraints, and computational thinking. The games I will be talking about are Tower of Hanoi, Mastermind Codebreaker, Move the Turtle, CodeSpark, and Lightbot. These games all are about creating structured environments where learners must reason through rules, constraints, and feedback. Research on game based learning supports this approach. For example, Qian and Clark 2016 explains games can promote cognitive engagement because they create environments where learners can actively test strategies and critically reflect on their thinking through iteration. I will be talking about how each game creates opportunities for learning and teaching. So, the first game I will be looking at is Tower of Hanoi. Tower of Hanoi is a logic based puzzle game in which students must carefully plan and execute a sequence of moves to transfer discs from the first tower to the third tower. So, there are two towers. The core rule is that a larger disk cannot be placed on top of a smaller disk. Because of this rule, every move has consequences, and students must plan their strategy before acting. So, in a classroom context, this game can be projected as a whole class problem solving activity. Before moving a disk, this teacher can ask students to explain their reasoning. In this way, the game encourages pre planning, pattern recognition, and sequencing. Another learning opportunity within this game is learning from errors. Instead of treating mistakes as failures, they become opportunities to trace reasoning. This game is best suited for grades 4 to 8. This game requires planning several moves ahead and connects to the Ontario curriculum in the sense of mathematical reasoning, patterning, and algebra and problem solving strategies. It would be cool as a whole class puzzle on the smartboard where students predict moves. So the next game is called Mastermind Codebreaker, and this game focuses on deductive reasoning. So this is more like a physical game where students use feedback on guesses to refine their strategy, which is the correct color versus the correct position. In this game, players must guess a hidden color code. And after each guess, the game provides feedback about whether colors are correct and whether they are in the correct position. The game works best with students between grades 3 to 8 because it focuses heavily on logical reasoning. The feedback system creates a structure where every guess becomes an active hypothesis the students can test and prove. Also, pairs or small groups allow students to solve the code collaboratively. So, research by Kailani, Newton, and Peterson 2019 highlights that game based learning environments are especially effective when learners are able to test ideas, receive feedback, and adjust their strategies. In a classroom environment, Mastermind Codebreaker can be used as an activity where students work in pairs and discuss questions that support metacognitive thinking. Um, Questions like what possibilities can we eliminate now help students reflect not just on the answer, but the process that goes behind it. This game is great in the sense that it mirrors the scientific reasoning process where hypotheses are formed, tested, and refined. So the next game is Move the Turtle, and this game works particularly well with the younger elementary students around grade 2 through 5. This is because it supports algorithmic thinking and the commands are very accessible and simple. Also, the visuals are solid and connecting it back to the Ontario curriculum. It supports early computational thinking and sequencing and logical reasoning. Students can predict commands before executing them. And in this game, the student programs a turtle to move across a grid using simple commands, such as moving forward, turning left, and turning right. Hisu and Hisu 2026 found that when elementary students are engaged in game based tasks supported by explicit guidance, they gain significant self efficacy. This reading is chosen to venerate the notion that sequence tasks help learners externalize their reasoning, which connects to move the turtle. As through revisiting algorithms, students can learn through iteration rather than trial and error. In the classroom setting, teachers can ask students to predict what will happen before running the code. If the turtle misses the target, students can then debug the sequence to see which command caused the error. Students can physically act out the turtle's commands with their bodies before translating those movements into code. This helps learners also learn through movement, symbols, and sequencing. So game number 4 is CoSpark, and this is a personal favorite of mine. CoSpark works across a wide range of elementary school grades, particularly grades 1 through 6. I actually had the opportunity to use CoSpark during my grade 5 6 placement at Da Vinci Public School in Toronto, where students explored the coding puzzles independently during learning centers. What I noticed quickly was how engaged students became. Because CoSpark removes the coding syntax and uses visual inputs and commands instead, students were able to focus more on the core logic of the problem instead of typing in real codes. So students were able to test an idea, see the results immediately, and then revise their strategy. They would often turn to their partner to say things like, wait, I think we need a loop here. Or, what if we try moving this command earlier? Research by Li, Chen, and Deng 2024 suggests learning engagement acts as a key mediator between game based learning and student motivation. So, this reading also articulates the importance of digital educational games and their roles in increasing student engagement and creating opportunities for exploration. The characteristics of interactive tasks and immediate feedbacks are explored extensively in this reading. So CoSpark exemplifies these characteristics through offering a low barrier of entry for a coding environment, and learners learn through playing, and that's exactly what allows students to experiment with commands, refine their solutions, conditions that research identifies as essential for maintaining motivation and deep learning in digital game-based environments. So one thing I particularly appreciated was there was multiple solution pathways for the games, and this provided immaculate opportunities for discussion about efficiency. CodeSpark also supports ELL learners and students with different learning needs because there are very little text in the games and prompts. And finally, the fifth game is Lightbot, which is great for students in grade 3 through 7 as it introduces functions, loops, and requires decomposition of problems. It serves as a stepping stone before real programming, similar to CodeSpark. As an educator, I would use Lightbot to see how students solve levels, then explain their algorithm. So the reading I chose, which was from Selmat, Nasir, and Anand, 2024, to describe computational thinking as consisting of the components of decomposition, pattern recognition, abstraction, and algorithm design on page 435. Lightbulb directly operationalizes these components by requiring learnings to learners to decompose complex tasks into smaller steps. So a key quote from the reading I chose that directly connects to the game of Lightbot is computational thinking consists of four main pillars: decomposition, which refers to breaking down identified problems into smaller parts; pattern recognition, abstraction through identification of important details and removing unnecessary information; and algorithm, where a step-by-step procedure is made on page 435. So in this way, students must break complex paths into smaller steps and create efficient algorithms using loops and functions. Because the robot's movements are visible, the students can easily identify where their logic breaks down and revise upon these strategies. So, in conclusion, a common pattern emerges from these five games, which is students must create environments where they can learn, plan, test ideas, interpret feedback, and revise their reasoning. So, game based learning in this context helps students develop essential real life skills like computational thinking and logical reasoning. Thank you for listening.
All right, let's get into visual spatial reasoning and low-text game design. When I looked at Sliced It, I started thinking about how the game teaches without really explaining anything in words. The main action is drawing a line to divide a shape into equal parts, as can be seen in the video. In turn, it's the action of drawing this line which becomes the learning. Dwyer talks about how children use lines as mathematical graphics, where meaning is built visually rather than verbally. In Slice It, the player's slice isn't just a random line. It represents partitioning symmetry and spatial estimation. You're essentially constructing mathematical meaning through drawing. Segdig and Sumner also describe how interacting with visual mathematical representation supports reasoning. In this game, you're directly manipulating the shape and getting immediate feedback. If it's uneven, you adjust. That trial and error process becomes the thinking. So instead of memorizing formulas, the player learns by visually testing their ideas. The mechanics themselves carry the math, and that's what makes it such a strong example of visual spatial reasoning. When I moved on to Cut the Block, I noticed that it takes the 2D partitioning from Slice It and pushes it into the third dimension. The main action in this game is slicing a 3D block to reach a specific target volume or percentage. Just like with Slice It, the game doesn't lecture you. It lets the mechanics do the teaching. Keon and Clark discuss how game-based learning provides problem-solving spaces where players can engage in exploration and discovery. In Cut the Block, every slice is a mini experiment. You're constantly forming hypotheses about where to cut the block so that it hits the target volume, and then testing those ideas in real time. One of the big things that Keon and Clark emphasize is the importance of immediate feedback. In this game, if your cut is off, you see the result instantly since the block falls away and the remaining percentage pops up. This low-stakes failure allows for what they call meaningful learning because you can adjust your spatial reasoning right away without the frustration of a wrong answer on a worksheet. By turning volume and 3D geometry into a situated active challenge, Cut the Block builds those 21st century problem-solving and critical thinking skills that are often difficult to evaluate through traditional testing. Now we're looking at 9 Holes. This game is a classic alignment puzzle, but it's much more complex than something like tic-tac-toe. Because once your 3 pieces are on the board, you have to move them to vacant holes to try to get 3 in a row. Nguyen talks about how we understand a player's cognitive process by looking at their emergent strategies. In 9 Holes, you can see this progress through a way a player moves from reactive play to anticipatory play. A beginner might just move a piece to block their opponent, but an advanced player starts to see the board as a network of potential paths. According to the research, these action sequences show that player is developing high-level problem-solving skills. The game creates a visual problem-solving space where you're constantly calculating your opponent's next move while also managing your own. The beauty of 9 Holes is that it teaches these complex concepts of spatial strategy and foresight entirely through the visual relationship of the pieces on the grid. As Nguyen stressed, by analyzing how a player navigates these constraints, we can see their learning in action, proving that the game itself is the assessment tool. When looking at Engel's Enigma, we're seeing a perfect environment for training, and what Utah considers a intrinsic dynamic spatial skill. This involves the ability to mentally transform and rotate objects. In this game, you're rotating interlocking circles to move colored gems into specific patterns. The research shows that these kinds of skills are highly malleable. Utah's meta-analysis found that spatial training has significant effect size, meaning that even short periods of play can lead to stable, durable improvements in how we process spatial information. In Engel's Enigma, the player is constantly performing mental rotations before making their move. This is exactly the kind of spatially enriched education Utah argues. By training the brain to visualize these complex movements, we're building the same foundational skills that predict success in STEM fields like chemistry and engineering. Finally, we have Monument Valley, which is a masterpiece of visual spatial design. The game uses impossible Escher-like architecture where you have to manipulate the environment to create paths. But beyond the geometry, the game is a perfect case study for what Mayer calls the emotional design hypothesis. Mayer explores how the effective features of a lesson, like appealing colors and shapes, can actually improve learning outcomes. In Monument Valley, the stunning visuals and calming atmosphere aren't just for show. They serve to increase the player's motivation and generative processing. According to the research, when a learner is emotionally engaged, they're more willing to exert the effortful deliberation needed to solve complex problems. The game follows what Mayer describes as the focused more is more approach. It uses highly appealing graphics, as you can see through the little video, to motivate you, but it's designed carefully so that those visuals don't become extraneous processing or a distraction from the core goal. Because the interface is so clean and wordless, it reduces the cognitive load, allowing the player to focus entirely on spatial reasoning required to navigate the impossible structures. It's a beautiful example of how emotional design can prime a student to tackle deep, challenging mathematical concepts without even realizing that they're studying.
What if failure weren't a setback but a signal, guiding players attempt by attempt towards stronger strategies and deeper learning? Learning, like gameplay, advances through iteration, each attempt generating feedback, each failure revealing information, and each revision sharpening strategy and eliciting feedback system response. In the game Ken, puzzles each move must satisfy strict constraints. No repeated numbers in rows or columns and correct cage totals, so every player action immediately reveals whether it fits the logic of the solution. When an entry is wrong, that failure becomes informative. It exposes violated constraints and narrows the solution space, turning mistakes into feedback rather than punishment. This reflects the principles of trial and error learning described in gamification and education, how it improves student learning. Across repeated attempts, players refine strategies, shifting from guessing to systemic constraint reasoning and pattern recognition, illustrating how repeated play improves decisions over time. As Hopkins and Carnico show in Which Games Are Fair, 2009, and how practices strengthens learning through the forward testing effect. Importantly, Ken builds mathematical reasoning itself. Reader, Thornton, and Venabush in Using Ken to Build Reasoning Skills 2014 show that solving requires candidate tests, elimination, and logical chains resembling proof. And because puzzles are intrinsically motivating recreational mathematics, they foster persistence and positive attitudes toward math, as Kulkarni explains in Recreational and Educational Value of Math Puzzles 2013. Ken puzzles engage students in structured logical reasoning with numbers of operations, building number sense, and fostering perseverance. Mathematical communication and multi-strategy problem solving in collaborative classrooms, because puzzles are intrinsically motivating and support algebraic and deductive reasoning through multiple solution paths and social solving. They help students develop positive math identities and deeper conceptual understanding, as depicted by Ryder et al. 2014 and Kulkarni 2013. As described in The Typing of the Dead by Appendor, the game replaces a shooter's weapon with a keyboard. Players must type words accurately and quickly to defeat enemies, so every stroke produces an immediate in-game consequence. Manuals and game documentation further show that errors or delays cause damage, missed streaks, or level failure, making feedback tightly linked to player action. Failure in the game is structured as a learning tool rather than an endpoint. When players perform poorly in drills or tests, they are directed to additional practice exercises that target weaknesses, positioning mistakes as formative feedback and encouraging repeated attempts. Found in Fandom, 5 Reasons games are a great way to learn typing. Across repeated play, strategy improves. Players refine touch typing, pattern recognition, and anticipatory motor planning as difficulty increases and performance metrics track progress, as found in the Typing of the Dead user manual SIGA. Lamb in Educational Game Critique 3, The Typing of the Dead, Overkill 2024, argues that the game builds real-world typing fluency by requiring fast, accurate input under pressure and disruption. Typing of the Dead transforms typing practice into humorous, high-engagement gameplay that builds speed, accuracy, and automaticity. through immediate feedback and repeated performance under pressure. Because players must type diverse words rapidly amid distractions, the game develops real world digital fluency while reinforcing skill through visible consequences in iterative practice. Human Resource Machine demonstrates how players construct simple algorithms by arranging command blocks that move inputs from an inbox to an outbox, so every program they design is executed step by step, making the system's response to player logic immediately visible. As Katz explains in Human Resources Machine, the official description by Tomorrow Corporation, Human Resource Machine frames the office as a simplified computer, memory tiles, accumulator, and instructions, so player actions directly determine computational outcomes. When a solution fails, that failure becomes diagnostic. James in Human Resource Machine EDU Review for Teachers 2018 notes that puzzles often leave players initially stumped, prompting them to return with revised strategies. Errors reveal flaws in sequencing or logic, mirroring real debugging practice in programming. Lapierre in Learning to Code with Human Resource Machine EDU 2017 adds that the game's step-by-step execution shows exactly where logic breaks down, turning mistakes into actionable feedback. Across repeated attempts, strategies become more sophisticated. Versailles in Human Resource Machine Teaching Coding Basics 2019 argues that players iteratively refine algorithms to reduce steps and improve efficiency. Human Resource Machine scaffolds programming concepts by gradually introducing commands and visualizing memory and control flow, helping learners connect concrete actions to abstract computing ideas. Through iterative debugging and optimization challenges, students develop computational thinking, metacognition, and algorithmic efficiency across differentiated skill levels. Dinosaur Polo Club in Mini Metro 2015 describes players as designing subway networks for a growing city in Mini Metro, drawing lines, adding trains, and reallocating limited resources as new stations appear. Every design choice immediately affects passenger flow and congestion, creating feedback loops between player actions and system behavior, which Beister highlights in Mini Metro Taking the Morning Train 2015. Failure in the game is diagnostic rather than punitive. When stations overcrowd and trigger a countdown to collapse, the resulting loss reveals exactly where capacity or routing failed. Overloaded lines, poor allocation, or neglected bottlenecks, providing actionable feedback for design, as explained by the Tab Guides team in Mini Metro Common Mistakes and How to Avoid Them 2025. Walker, in Learning from Mini Metro 2014, argues that these breakdowns make abstract transit concepts like capacity and demand visible, supporting systems thinking through productive failure. Across repeated runs, strategies evolve because each city grows differently. Players must iteratively restructure networks and optimize resources rather than reuse fixed solutions. Mini Metro engages learners in constructivist, systems-based thinking as they iteratively redesign transit networks in response to changing constraints and demand. Failure acts as a formative feedback, prompting strategic adaptation and metacognitive reflection about capacity, geography, and resource allocation. Factorio demonstrates how complex system learning emerges. As Whoop Software explains in Factorio Build and Maintain Factories 2015, players mine resources, automate production lines, and scale factories toward launching a rocket so every layout decision directly shapes throughout logistics and environmental impact. The game world dynamically responds to these choices. Expansion increases pollution and enemy pressure, creating continuous feedback between player design and system behavior. Failure in Factorio is concrete and diagnostic. Orndorff in The Factory Must Grow and So Must Your Engineering Intuition 2025 describes how bottlenecks, shortages, and overwhelmed defensive visibly expose flaws in system design, turning breakdowns into actionable information for redesign. Alam in Factorial Taught Me Systems Thinking Part 1 2025 argues that living with these consequences teaches modularity, scalability, and trade-off evaluation as players decide whether to expand resources now or plan for long-term efficiency. Across repeated play, strategies become more sophisticated. Alam notes that players naturally adopt iterative, agile-like development, building initial factory versions, testing them, and redesigning for scale as new technologies unlock. Factorio teaches systems engineering by making players experience the consequences of design decisions, revealing principles of modularity, scalability, and throughout optimization through experimentation. Iterative factoid design and resource trade-offs mirror agile development and engineering planning, fostering strategic prioritization and continuous improvement.
My section includes 5 different games, and let's start with Minecraft. Minecraft provides several effective learning opportunities for teaching. It allows students to work together on large building projects. In this case, they can share ideas, divide tasks, and solve problems as a team. This helps improve their creativity, communication, and teamwork skills. Building in a 3D world also facilitates students to develop spatial thinking and math ideas such as volume, scale, and symmetry. In addition, managing resources teaches students to plan wisely and make sustainable decisions. Most importantly, Minecraft supports learning across many subjects. Students can build historical sites, study ecosystems, practice storytelling, and learn basic coding. This makes Minecraft a very useful tool for creative and effective teaching. My next game is Roller Coaster Tycoon. Xioid discusses that it is Roller Coaster Tycoon that offers a fun way to practice financial literacy and basic economics. By running their own theme park, students make decisions about prices, budgets, income, and expenses. They can clearly see how their choices affect the park's success, making abstract economic ideas practical and easy to understand. This game also fosters design thinking and spatial planning. Players arrange rides, paths, and facilities to keep visitors happy and the park running well. This helps them learn about user experience and how to create functional and enjoyable spaces. In addition, the game teaches adaptability and responsive problem solving. Students have to deal with changing things like fewer visitors, broken rides, or a tight budget. They learn to adjust their plans based on real-time feedback and make quick, smart decisions instead of just following a fixed plan. As a result, this makes Roller Coaster Tycoon a useful game for building practical life and thinking skills in students. Now let's take a look at LEGO World. Freeman describes LEGO World as a platform which encourages open-ended exploration, which lets students discover and create in a large, flexible LEGO world without strict rules or fixed tasks. This helps learners take control of their own experience and develop independent thinking. What makes LEGO World special is its easy-to-use discovery tool. Students can quickly copy and reuse objects, making building simple and enjoyable. By this way, they can focus on creativity rather than struggling with complex steps. The game also supports creative roleplay and storytelling. Students can interact with different characters, change the environment, or invent their own adventures. These activities help improve imagination, communication, and self-expression. Next is Tabletop Simulator. Unlike other games, it recreates real board game experiences online with realistic details like moving pieces, rolling dice, and shuffling cards. This lets students practice taking turns, communicating, and building social skills even when they are not in the same room, by playing games like chess, poker, or classic board games. It also helps develop tactical thinking and decision-making skills. Many games on the platform require students to plan strategies, guess possible outcomes, and make choices together. Since the game doesn't enforce rules automatically, they have to talk, negotiate, and work as a team. As a result, this game boosts their logical thinking, teamwork, and ability to interact responsibly in a team. Finally, let's turn our attention to Kerbal Space Program. Rosen states that cognitive simulations like this make learners interact with complicated ideas safely, making hard domains like spaceflight far easier to understand. This game also lets students build and launch their own rockets, learning physics through real experimentation rather than just textbook lessons. They observe exactly how thrust, weight, fuel, and gravity work together, and a flawed design will keep the rocket from reaching orbit. This immediate feedback makes abstract scientific ideas tangible and easy to grasp. Mission planning and resilience are also key learnings here. Most first launches end in failure, but every tiny mistakes teach students what to adjust and improve in the future test. This process builds patience and teaches them that failure is just a vital step in the design and journey to success. It is a core benefit of interactive simulation. Generally speaking, it's a fantastic tool for making physics and space learning engaging and practical for students.